September 21st, that's pretty soon, isn't it?
Very soon. Thanks, Stuart. Appreciate it.
We're going to dim the lights here.
I appreciate the opportunity to come and share with you a little bit about the science of this mission. How many of you have heard of MAVEN? Wow, that's awesome. I am not Dave Braden. I want to preface all of my comments now by the fact that I was selected by NASA to serve as one of approximately 30 Educator Ambassadors on this mission. Our primary responsibility is to provide information on the mission to educators so that this can then be disseminated out to students around the country. Dave Braden is a professor and researcher at the University of Colorado, Laboratory for Atmospheric and Space Physics, which is one of the two schools or two primary institutions that are involved in this mission. And I want you to know that the slides that I'm using tonight have been provided to me by these investigators, and their names are credited accordingly. MAVEN is a unique mission in that it does not have all the bells and whistles that we have come to expect on most Mars planetary rovers. There will be no cameras. There's going to be no pictures sent back that can show up in Time magazine and National Geographic, etc. This is strictly a science mission. It was launched on November 18th of last year. I understand there was someone else along with myself who, were you there also for the launch of that? It is going to go into its orbital insertion on September 21st, which is now just 16 days away. I would also point out that at about 4 o'clock this afternoon, I had the opportunity to participate in a web conference with Dr. Bruce Jakoski, who is the principal investigator for this mission, to give people an update on MAVEN's status and where things are. Interestingly, when this mission was launched back in November, as is the case with any spacecraft that is being sent to Mars, there is a specific launch window that coincides with when the two planets are in the proper alignment so that we can get a vehicle from here to there. Usually that window has a nominal launch period of about 6 weeks, during which you have a 2-hour period in each day that they can actually light the candle. And they go off in 5-minute increments during that 2-hour period. If it doesn't go, they wait until the next day and start the process again. MAVEN was launched in the first 5 minutes of the first launch window on the very first day. And that was kind of a cool indication of things to come. And according to Dr. Jakoski this afternoon, MAVEN is basically in trajectory with all operating systems going. They had actually planned on 4 course corrections during the travel time. They've only executed 2 because everything else was running smooth as silk. So the entire MAVEN team is pretty stoked right now with the idea that they're going to be ready to start collecting data just as soon as this thing can go into its orbital insertion. So let's start with Mars today and what we know. People are accustomed to seeing photographs now from rovers, from the Mars Reconnaissance Orbiter. We know a lot about the geology of this planet. We know that it contains very large volcanoes, that it contains immense valleys and chasms. We know that there is a heavily cratered portion of this planet. There's also indications of things going on that must have been caused before now. And this is really where the curiosity has been piqued. I kind of like this photograph. This is actually of one of the ice caps of Mars. This is a process of wind effect that occurs while the principal carbon dioxide is frozen during the winter period, and you actually have wind carving this out over the ice. We have evidence of amazing formations that clearly had to have been formed by some type of liquid component. We also know that the atmosphere is in fact pretty active right now. These were taken by, which one?
Spirit.
Spirit or Opportunity?
Spirit did that.
Yeah. Leaving patterns like this on the surface. So here we have a planet that we know something about today. Interesting geology that definitely appears to be caused by the influence of water. We've got sedimentary soils that have definitely been layered over time. And of course, if you're familiar with the Mars Science Laboratory, you know that this picture was taken inside of Gale Crater. The intent, of course, of curiosity is essentially to go somewhere up there over time. So, here's what we know about the Mars atmosphere today. It's cold. It's definitely toxic, at least by our description of what would be necessary to keep us alive, and it's incredibly thin. How thin? Roughly 1% of our atmosphere is present there at this time. But there is a lot of evidence that Mars was different in the past. Here you see channels that form into larger channels that basically were produced by water, liquid water, that had to have been there for an extended period of time. We see deltas that were formed by this water outflowing over time. We see the effect of both water and wind. And the wind would have to be even much greater than what we saw in those previous slides, where you have some turbulence going, but not creating much of an effect. But then we start to look at things a little bit differently. And this is one that has the MAVEN scientists especially interested. This was taken by the Mars Reconnaissance Orbiter, and these colored areas show signatures of both iron and magnesium phyllosilicates. A geologist would tell you that the formation of those two minerals can only occur in a water medium. And it had to have occurred over an extended period of time. So, the question that MAVEN hopes to answer, at least contribute more knowledge to, is this. In order for water to exist in the liquid phase, you have to have both an appropriate temperature and an appropriate pressure. The atmosphere today is so thin that any water present on the surface sublimates automatically. It goes directly from ice to a gaseous phase. And that is occurring in very small amounts, especially during the Martian summer of the northern hemisphere, because the northern ice pole does contain quite a bit of H2O. But for it to have been a liquid, to have produced the type of topography that they see and know exists on this planet, you had to have an atmosphere that was thick enough to create adequate pressures combined with temperature that can only be retained by that atmosphere for extended periods of time. Millions of years, tens of millions of years, those are questions MAVEN probably won't be able to answer, but it will be able to contribute to where did all of that go. So basically it comes down to this. The atmosphere and the water contained therein either went up or it went down. It's been absorbed into the soils or it has been lost completely from the planet. MAVEN's primary mission is to study the atmosphere and hopefully gather enough data to then extrapolate backwards in time to understand the length of time and the process that was involved in eroding away the volatiles or the gases of the atmosphere that allowed Mars to exist as it did previously. Now, what causes the ups? Unquestionably, the primary contributor will be the sun. And in fact, most of the instruments on MAVEN are going to be studying the sun itself, not the planet. Of the primary instruments on board, there are 8. 5 are not even going to be looking at Mars. They're going to be studying the sun. One of the reasons that MAVEN was launched at the time that it was, well, the real reason it was launched is because NASA said this is when you can go, truthfully. But ideally, the scientists would tell you that this is when they wanted to launch because of the solar cycle. It turns out that the solar cycle will have peaked and will be starting to diminish during the year of science that MAVEN is primarily commissioned to study. But that is also the period of time historically when most of the solar activity is occurring. And they're hoping that with lots of coronal mass ejections and other activity, that will contribute to the study of the ions and the solar wind that they're going to be analyzing with this spacecraft. So, why is this important? Well, most of you are probably aware of the fact that Mars is now considered a frozen planet, meaning it no longer has an active magnetic dynamo. It does not have a unified magnetic field around it. Therefore, it does not have the protective shield that Earth does. Any solar material can interact with the volatiles that are in the atmosphere much more easily. So, the theory is that at a time in the past, Mars was much more like the Earth. In a younger state, with a quasi-solid molten core that is both moving and convecting simultaneously, which is what's necessary to generate a planet-sized magnetic field. Mars probably had the same process protecting it that we do here on Earth today. But over time, that was lost. That process was stripped away. Most likely, the contributor is the lack of that unified magnetic field. So, the questions that are being asked, you can read them for yourself. There are a lot of theories. and the instruments are designed to test those theories. And I think that right now, in light of a lot of things that we see happening on Earth today, one of the questions we have is, what can we learn? Those of you who may have an interest in comparative planetology probably know that right now the trinity of Venus, Earth, and Mars are being looked at in terms of global warming, climate change. We have two partners that can kind of show what can happen on either end of the spectrum here. What can we learn from that here on Earth? So here we are with MAVEN. Now, a little background. MAVEN stands for Mars, Atmosphere, and Volatile Emissions. The N, yeah, it's interesting how they come up with these acronyms. It is designed to study the evolution of this atmosphere. So, the spacecraft is oriented with instruments on both ends of the solar arrays here, on two booms with multiple gimbals that will allow them to direct the instruments in the direction they want, which is primarily away from Mars directly, back at the Sun, along with, of course, a high-gain antenna here in the middle so that they can communicate with the Earth. These are the instruments that are on board. Rather than going through each one of them individually, I'll tell you that virtually all of these are spectrographic in nature. They're going to be looking at ions. They're going to be looking at isotope combinations to determine how much of different substances have been stripped out of the atmosphere, at what rate, in order to determine what the effect of the Sun has been on the planet. So this is actually a slide that is used by the MAVEN team a lot to encapsulate this process. We know that the Sun, through coronal mass ejections and charged particles, is constantly emitting material that can interact with an atmosphere. Due to the lack of a unified magnetic field around that, there are a number of different mechanisms by which those ions can interact with primarily ions in the ionosphere itself and strip them away. So you actually have a number of different methods of atmosphere loss, and each one of these is going to be analyzed by instruments on the spacecraft to determine which ones are most prominent, which ones have contributed the greatest impact over time. You'll notice, by the way, I just want to point this out, that there are magnetic fields in the planet. And this is an interesting component. It basically has to do with the fact that there are magnetized regions within the crust of the planet caused during that era of early unified magnetic fields that are still causing kind of a localized effect of protecting certain areas of the planet. So, MAVEN fully look. I'm sorry, go ahead.
On the previous slide,
Yeah.
you had Gene's escape. Can you explain that?
Gene's escape is essentially basic physics. It has to do with the fact that any gaseous component, a molecule, atom, whatever, can achieve escape velocity due to an adequate temperature and pressure. So kind of using Maxwell's constant, you can establish an average, and then anything above that average, you have sufficient energy, E equals 1/2 mv squared, to escape the planet's magnetic pole.
Okay.
So that's happening everywhere. I mean, that's happening here on Earth, right?
Sir James Jeans, I assume?
Yeah.
Okay.
Right. As an interesting aside, curious that I discuss this with my students a lot. Do anybody in the room have an idea on what gas is most prevalently lost to the atmosphere of Earth these days?
Helium?
Exactly right. Yeah. It's a very interesting thing. Helium is becoming a precious commodity. In fact, so much so that the largest consumer of helium, which is the Macy's Thanksgiving Day Parade, now recaptures all their helium when they deflate those balloons. From year to year, they're recycling that stuff because of the fact that, of this effect. I mean, it's a very light element, and when it attains enough height, it's got sufficient escape velocity to, it's gone.
You're thinking of restricting the sale of that.
Yeah, yeah.
I would expect hydrogen.
Well, I understand that it's helium. I mean, I understand hydrogen would be the same thing, but we have a much greater abundance of hydrogen. We've got a pretty limited amount of helium, relatively speaking, to the
Well, that's it. Helium doesn't interact with other elements as much as hydrogen does.
Right.
So you're asking just which gases would be lost, or that we're seeing less of because of this.
Exactly.
In that case, okay.
Yeah. Any other questions? So the MAVEN spacecraft, fully loaded, meaning with its full complement of fuel, weighs approximately the same as a GMC Yukon. And as I understand it from today's web contact, that means a GMC Yukon that has a full tank of gas, 4 passengers, and about 200 pounds of camping gear in the back. With the solar arrays fully deployed, it's got a profile equal to that of a school bus. So it's a pretty good sized spacecraft. And here you can kind of see these arrangements where, again, the magnetometers, and there are 2 of them, are placed essentially on each end of the solar arrays to get them as far away from anything on the spacecraft itself that might kind of create an artificial signal for them. But the primary instruments are located either fixed in this area right here that will be directed towards Mars itself, but most of these are on these articulated arms out here, and these Langmuir probes that run off basically kind of analogous to an old pair of TB rabbit ears that can then be directed no matter where it is in its orbit around the planet to keep them oriented more towards the sun. So it was launched March 18th. It basically used a trajectory around the sun and will arrive
Your slide says
here.
November.
Excuse me, what did I say?
It says November. You said March.
I did, my bad. November 18th, 2013. And it will be inserted over here. And by the way, I'm obliged to point out that this is not to scale. Mars is a little bigger, and MAVEN is a little smaller than that image indicator. Right now, it's commissioned for 1 year of science operation on this type of an orbital trajectory. At closest approach down here in periapsis, it will be approximately 90 kilometers. So it will be well within the atmosphere of the planet. It will be in situ so that it can gather data. They actually have a variable trajectory so that they can dip to as low as, I believe, 45 kilometers. They have 3 of those passes planned, and I'm sure the people are going to be going, please don't hit. And at apoapsis out here, it will be about 4,000 kilometers from the planet. So, we compare Mars to the Earth, and we know we have this magnetic field here. This is Dave Brain's approach because his focus on this is really the role that the lack of magnetism has been playing. So, if we look at a magnetic field, this is Earth. If we were to take the sphere, flatten it out onto a 2-dimensional plane like this, you can see the orientation of Earth's magnetic field. We compare that to Mars. Oops. First of all, reading graphs, you know, you have to pay attention to the details. It is important to note here that we're talking about a magnetic field up to as many as 50,000 nanoteslas. On Mars, nothing at all in that range. But if you were to reduce that down to a much smaller frame, such as a magnitude of only 200 nanoteslas, we start to see this. And this is kind of an interesting thing if you know the assumed formation and topography of the planet. Here's Mars, flattened out into 2 planes, northern hemisphere and southern hemisphere, right? If we look at this, you might see something in a pattern. Am I going right there? There. Now I want to go back and forth on this to kind of emphasize a point. Again, 2-dimensional map of a 3-dimensional sphere. Northern hemisphere, southern hemisphere. The prevalent theory is that Mars and Earth's moon are quite similar in many respects. It is believed that this is probably original crustal material. These would be analogous to the lunar highlands. This is a much higher topography than you find up here in the north. This is also volcanic in origin. It's lava fields, which means geologically it's much younger strata. So if we go back now and look at that, where do we see those magnetic fields embedded into the crust? They're there in those ancient soils, the ones that have probably been unchanged for billions of years. The same thing happens here on Earth. We know of magnetic flips in the Earth. We know that because of the rock records. We have things that are oriented in different directions. That material was delivered to the surface volcanically and then eventually solidified. One of the problems with that is that you can break down a magnetic field under intense heat. So here what you have is in the southern hemisphere of the planet, in this highland region, you've got a much more localized magnetic field. How much of a role might that be playing in the preservation of any atmosphere that still exists on the planet? That's a question that Dr. Brain, I love that name, by the way. Good afternoon, students. I'm Dr. Brain. Wouldn't that be? Yeah, it does. Okay. So where did the field go? This is the idea. In terms of a unified field, it's basically how big is the potato? How rich would the interior be in the radioactive components that are still primarily responsible for the heat generated from within the Earth, right? Chemically speaking, Mars should probably be a lot like we are. I mean, you would consider the concentrations of heavy elements and even radioactive ones to probably not be too much different than you would find here, than you would find on Venus. So if its magnetic field is shut down because it simply lost sufficient heat to keep the core molten, it's due to its size, it's due to its mass. So, now let's turn our attention in a different direction. Matt Fillingham is at the Space Sciences Laboratory at the University of California. This is where I was sent to get my training on this mission. It's kind of nice to go to the San Francisco Bay Area and spend time there being trained. Here's what we know about Mars's composition at the present time. The atmosphere is almost exclusively carbon dioxide, less than, way less than 1 bar of pressure. This results in surface temperatures that range from lows of -143, actually getting up to, in equatorial regions at certain times, right about 273 degrees Kelvin, right about the freezing point of water. If it were Earth, then you had 1 atmosphere. Unfortunately, there you don't have 1 atmosphere of pressure, so even if there is water present and it's exposed, it's just going to sublimate. It's just going to go straight to the gas right off the bat. So, the present theories about where do atmospheres come from? They're definitely due to impacts. We believe very strongly that a lot of the water delivered to Earth, that we have here on Earth, was delivered. The isotope ratios seem to suggest that that's matching pretty well with a lot of the comets. There is outgassing on a large basis and a continual small basis. And then, of course, there's evaporation and sublimation. That's how you get an atmosphere. Mars has all of those components. We all know that Mars has the largest volcano in the universe, and it had to have been active for a very long time to build up that much of a stratum. We also know that presently it's still contributing because of the change in these polar caps. And now it does seem as though at least the northern polar cap contains a fair amount of water. It was thought for a long time that it was basically dry ice, mostly frozen carbon dioxide, and the southern polar cap seems to be predominantly that. But there is an abundance of water in this ice as well. This is an interesting slide that kind of looks, based on Mars days, the change in surface pressures as measured by the 2 Viking landers back in the 70s. And when we get up to this point right in here, the surface pressure combined with temperature might even lead to droplets of water. And that was a pretty tantalizing piece of information. There's still water there. But liquid water can't exist on Mars today. It's simply too cold. The temperatures are way too low. So the question is, where did all that water go? How much of it was lost completely? And how much of it is still retained within the soils of the planet and in the caps today? So when we go back to this idea of liquid water having been there before. We see all of this channeling. There's all of this evidence of huge volumes of water. What I've heard reported is the analysis would suggest that Mars at one time had more liquid water on its surface than Earth possesses today. Think about the size of Mars compared to Earth. I mean, this might literally have been a water world. Of course, the ubiquitous blueberries, I'm sure most of you are familiar with those, can only form in a liquid environment. I just like that picture. I think it's beautiful. So here's the thought. Did Mars once look like this? Now, from a planetary science perspective, of course, the real question is, if this is the way Mars was, what happened then? Is there going to be any evidence that life may have even initiated during that period of time? I mean, that is the driving underlying question. Are we alone? But now we know that Mars has kind of undergone a major change. And this is where we are today.
Wouldn't the water have hit the triple point? Or in other words, if you take all the pressure off of water, first it turns into a gas, but that gas takes heat with it and it freezes.
Yes. And conversely, by definition of the triple point, you could have water in all three phases simultaneously. Right? But I think that the idea is that, as you said, it's taking energy with it.
Oh, yeah.
If that energy is then being used kinetically, you may have sufficient energy for it to simply be lost. And that's one of the questions. How much of that water is no longer there?
How fast did the atmosphere,
I'm sorry.
how fast was the atmosphere lost too? If it's lost over a short period of time, it might get freezing. But
That's probably the question that I think the MAVEN investigators feel most confident that they'll be able to answer. They do believe that they have a year's time. As with any of these missions, if the spacecraft is operating competently, if all the instrumentation is working at the end of 1 year, they'll apply for an extension and they'll get it. You know, it's just kind of that unwritten rule. Why would you shut something off if it's functioning properly? They've never done that on any mission to Mars. They're not going to do that here. But they do think that with even a year's worth of analysis, by basically looking at how much solar activity is stripping away at the ionosphere now, what's the loss presently in volatiles, and then using their models to build back and extrapolate at what point in the past did all of this change dramatically. I think they will be able to answer that. So you keep an atmosphere principally through gravity. And that's one of the things that kind of gets lost in a lot of this, because everybody's focusing on solar activity and the loss of a magnetic field, but at the same time, you can't ignore the simple reality that a planet the size of Mars, because of its gravity, has a much lower escape velocity. So this material is going to find it much easier to just radiate back out into space than it will here.
That would be the problem with life there, since you'd be losing your atmosphere rather rapidly. Life would exist only for a short period of time if it existed.
Exactly. Temperature. You have this magnetic field, and this mission is really not going to be focusing its attention on that. I mean, the magnetic field of Mars is pretty well understood. There will be some analysis of it. I think there is some question, how much of an effect do these localized magnetic fields have in retaining or providing some protective effect in those regions, but that's really not where we're going. So what they're going to be looking at is the escape of neutrals, primarily the ion and plasma effects in the ionosphere itself. That's what they hope to answer with this mission. So in reality, you'll find that the instruments on board are basically looking at this effect and the stripping from the solar winds. This is kind of a, there is actually a great 3D model of this in video form that kind of shows this effect. But essentially, the idea is that you have this stripping that is probably removing most of the ions and, you know, the neutral particles that are still in existence. So we see the difference between Earth's Van Allen belt and what they know presently exists. Point out that the color coding basically is a bipolar effect. It is a north-south. Blues, I think, are north poles. Reds are south poles. So you could kind of imagine a magnetic field between those. Would be kind of like what they show on the sun with so many fields going out entangling.
So the theory is that's ancient magnetic field that's frozen into...
It is frozen into the soil.
rocks.
Exactly right.
Like we find
They will remain magnetized.
We find magnetite in places here on Earth.
Exactly. Exactly right. I mean, the only thing that would change that now would be impacts.
Or if you had volcanoes in those regions.
Unfortunately, you don't have anything to...
Yeah.
Yeah, that's the issue.
But that would be another case where it could happen.
Exactly. Now, there are these reactions with the soils themselves, and as I said, impacts. So we kind of come back to this, and you now have this same thing showing that all of these instruments right here are going to be analyzing the sun in terms of Septs and coronal mass ejections, while the instruments over here are going to be looking at plasma processes. And at that, I'll leave you with this picture of MAVEN and open it up to any questions.
When you're pointing it, obviously you have to point it at the sun if you want the solar rays to get energy. But if you want to talk to the Earth, you have to point it at the Earth. And if you want the planet, you have to point it at the planet. How do you move the sucker around?
Hydrazine is the gas that they will use. Although the solar arrays will be oriented towards the sun. Within this compartment here, the central piece, there are instruments mounted essentially on the backside that will be directed at Mars itself. Because again, we're going to have this pointed primarily sunward, And unless we're, you know, in a specific area trajectory, that's also going to put your high gain antenna directed towards Earth. Now, they won't be able to communicate constantly, but you're absolutely right that you've got to have that directed back here in order to send it. Now, that's why these two booms that have multiple gimbals on them have most of the instruments mounted there. That way they can keep swiveling this in whatever direction they want, you know, to align it with solar winds and, you know, the movement of plasmas. Yes?
Does the solar wind leave anything behind as it's coming through as well as taking it away?
I don't know.
Okay.
I can't say. But and jump in here, but I mean, the solar wind is a constant. I mean, it's really more a matter of the concentration, you know, rather than it, you know, kind of coming in waves. I mean, it's a fairly constant thing, so it's kind of like, you know, the flow of a river. Once it goes by, it's
primarily protons and
gone.
electrons.
It is primarily protons. And, I mean, it's charged particles.
It's charged particles.
Yeah.
It's basically hydrogen atoms that have been split
Right.
as they leave the sun.
Exactly.
And you haven't had time to recombine the atoms of gas.
Jack, you got any thoughts on that? You know, with the effect of the solar, can you see the solar wind depositing anything or leaving something?
Well, that is a good question. It's probably going by at such a high velocity that it would rather take them than give them back.
Yeah. I don't know, but my inclination would be not. I would really describe it more like the flow of a river.
Yeah.
You drop a stick in, it's just going downstream. It's
Well, yeah, you have more solar wind piling in from behind that pushes
Right.
out yesterday's solar wind.
I mean, the differences there would be in the event of coronal mass ejections or something else that's simply dumping out a lot more mass in a short period of time.
You would think it'd be like a fire hose that would just take it off faster.
Exactly.
And I don't know about turbulent, you know, coming around the back of the planet maybe, but
Yeah, and there is some of that actually. I mean, there as it is, it's kind of, you know, the same thing as you think about the aurora effects here on Earth, where essentially you have this backflow and these things are being pulled down in towards, you know, both polar regions. So you would have that effect, but in this case, it would be.
How can you, if there's not a significant magnetic field, you're going to have direct solar wind impact on the surface of the planet,
that's
but
right.
you're not going to have the magnetic field pulling particles back in over the poles.
Yeah, the polar aurora, that's strictly a magnetic. They get
Right.
caught in the magnetic field basically, and they follow the magnetic lines of force.
And the solar wind, if you think of the solar wind as a gas, it's actually a plasma. There are protons and electrons, charged particles, so as a whole, it's basically neutral. But it's not going to, it is much more tenuous in the Mars atmosphere, even though the Mars atmosphere is nothing compared to Earth. Solar wind is less yet, so
Oh yeah.
the only effect is going to be really on the very outside of the Martian atmosphere. You might temporarily slow down some of those particles. Some of the protons and electrons may recombine into neutral hydrogen, whereupon some other proton will come in and collide and break up the. So you might have a slight elevation in neutral hydrogen toward the outside of what you can measure.
That sounds exactly like one of the questions MAVEN should be looking into.
Duly noted.
Why does MAVEN need so many instruments looking at the solar wind? Don't we have enough detectors and satellites on both sides of the sun and all that?
Well,
Not at all.
I think that they're doing this with the idea of being in the region of Mars and seeing what that effect is there. Again, it kind of goes to this idea of why they were looking to launch at this particular time. You might recall, right about the time of this launch, Uncle Sam threw a monkey wrench into the works. They called it sequester, and they shut everything down. They got special dispensation on this one. You know, someone made a phone call, I guess, and they were basically told, okay, you know, even though we're not spending any money, we'll let NASA go in and launch this thing, assuming that, you know, the launch parameters were right, because they want to be there with the idea of, you know, high solar activity.
How much did it cost?
In round numbers, it is on the order of $2 billion. This is what's called a medium-sized program. This is not Curiosity, but it was competitive. Interestingly enough, there were two different proposals submitted simultaneously. Both of them basically made it to the finish line. This one squeaked by. The other proposal also came out of CU last. So it was literally guys in one office against guys in the other office. And as I understand it, they're now all talking to each other. But there was a period of time when there was a certain amount of, yeah.
Talking to each other with four-letter words.
Any other questions? Well, thank you very much.
Thank you.